Hi, in today's video we're going to talk about atomic weight. So today we're going to learn about the relative masses of the different subatomic particles we discussed last time. We're going to define the atomic mass unit, and we're going to define atomic weight, and as we always do, we'll do lots and lots of examples. The purpose of this slide is to just review with you quickly the fact that we have the proton and the neutron that are found in the nucleus, and the electron also in the atom, but in the electron cloud. And today, for the first time, I want to show you just how small these particles are. The proton and the neutron both have mass on the order of around 1.7 times 10 to the minus 7 kilograms. The electron is orders of magnitude less than that, much smaller. So notice that the mass of the proton and the neutron are almost the same, and the electron is quite small in comparison. And just to give you an idea how small we're talking about, these particles, the proton specifically, is as small, if you look at its power of 10 here on this scientific notation of its mass, as Jupiter is large. So if you want to think about 27 orders of magnitude going either direction here, that just gives you kind of an idea how small we're talking about when we say the proton is small. Because of that, it becomes necessary to define what we'll call the atomic mass unit. It's not convenient to talk about 1.7 times 10 to the minus 27 kilograms. That mass is much too small to be practically important in any common sense. If we want to discuss these masses more comfortably, more conveniently, we want to define the atomic mass unit. And so notice this is a contrived unit that we just kind of made up, and as chemists. And what we do is we define the mass of carbon-12 as exactly 12 AMUs. And so what we're going to do then is describe the mass of every other atom relative to carbon-12. When we take our masses of the proton, neutron, and electron that we discussed last time, and then rather than discussing them in terms of kilograms, we can convert them to atomic mass units, or AMUs. Notice that we go from talking about something that's 1.673 times 10 to the minus 27 to we can say, oh, it's 1.007 AMUs, approximately 1 AMU. So notice the mass of proton and neutron is about 1 AMU, and again the mass of the electron is much smaller than that, orders of magnitude smaller. Remember, we're not changing the mass, obviously, we're just redefining how we talk about it. This unit is much more, remember, the key word here, convenient, much more convenient to use this mass than it is to talk about grams or kilograms when discussing such small entities. So having defined the atomic mass unit, we're now getting ready to talk about atomic weight. And so if you look at the periodic table, you see some kind of entry like this for carbon. Okay, and what do we see here? We said last time this number here refers to the atomic number. Well, the mystery is, what does this number down here mean? That is the atomic weight. When we say atomic weight, we are discussing and talking about a weighted average of the mass of all of the naturally occurring isotopes of carbon. If you look at carbon, there's two different naturally occurring isotopes of carbon, carbon-12 and carbon-13. We discussed these in our last video. And notice that carbon-12 accounts for about 99% of all carbon, while carbon-13 makes up the other 1%. And so if you could visualize here this kind of a grab bag, if you will, of carbon atoms, about 99 out of every 100 are carbon-12s, while only 1 in every 100 is carbon-13. Well, as chemists, we're rarely doing experiments where it matters too much whether we have carbon-12 or carbon-13. In fact, what we're more likely to do is grab a trillion molecules and do an experiment. Okay? And so it becomes important for us not to discuss the mass of any one particular atom, but rather to discuss what the representative atom might be. So when we compute the weighted average, or the atomic weight of carbon, we take a weighted average of each isotope according to its abundance. And so just to tell you here and to show you how this is done, we'll say that the atomic weight of carbon is equal to the mass of your first isotope, which mass, remember, carbon-12 is defined by definition as being exactly 12 AMUs. So we can say that the weight of the first isotope is 12 AMUs exactly. Okay, and remember that isotope was about 98.93% abundant. We're going to change this back into the decimal form of the percentage, and it has no units. And then the other isotope, carbon 13, has a mass, if you want to rewind it or whatever, or just trust me on this, has a mass of 13.003. 35 AMUs. I'm looking at my notes here. Okay, and this guy here accounts for about 0.0107 or 1.07% turned into a fraction. Alright, so this is the weighted average. Now I must compute this weighted average using the rules for rounding that I learned in the previous modules. And here it's asking us to take 12 AMUs and multiply by 0.9893. When you do that, you get that the atomic weight is equal to 11.8716 atomic units. And notice I have 1, 2, 3, 4 significant figures in this measurement, and I have an infinite number of significant figures here. So I'm going to round this to 4 sig figs here. So I'm eventually going to round here, but I don't want to do that yet. For the next term here, we have to evaluate this product here, 13.00335 times 0.0107, and we get 0.9136. Okay, atomic units. And again, we have to count and figure out how to round this. We have 3 sig figs here, 1, 2, 3, and we have a whole bunch here, so we're going to round this to 3 sig figs here. So when we add these together, we get 12.01074 atomic units. So we can say that the atomic weight of carbon is 12.01 atomic units. So just remember, when we talked about our previous example, not one of these carbon atoms in the grab bag had a mass of 12.01 units. Instead, what we said was the carbon 12 had a mass of 12 units, and carbon 13 had a mass of about 13 atomic units. So not one of them has a mass of 12.01 atomic units, and yet we don't really mind too much, because remember, we're not going to be working with single atoms all that often. And if you ever have to work with single atoms, if you're a particle physicist or something, well then you would use the mass of the atom of interest. The next example just shows you that this idea of a weighted average is used in your everyday life. This is not just something that chemists made up to talk about atomic weight. This idea should be very natural to you. And imagine that we have a student who is taking a chemistry class, and they have homework grades, quiz grades, and exam grades. And let's suppose that the syllabus describes that the grades are going to be weighted in this fashion. So the grade is going to be 10% of the homework grade, 15% for the quiz grade, and 75% for the exam grade. And a generic student, Joe, happened to get these scores right here on his scores throughout the semester. The chemistry professor then, or the TA, is going to compute the grade using the weighted average that we talked about. So Joe's score in chemistry class, his grade, is going to be found by the weighted average formula that we discussed. So first you'll take your homework grade that you got here, and the 10% that the homework is worth, compute it into a decimal, times Joe's homework score. Joe didn't do too well on the homework score. He got a 65. Okay. Next, you take his quiz score. Did much better on the quizzes. These are worth 15%. And he got a 93 on his quizzes. Next, on the exams that are worth 75%, he got a 90 on the exams. Alright, and when you, excuse me, this should be 0.75. When you compute this grade here that Joe got, he got, when you work this out, you end up with 6.5 for this component, and then 13.95 for this component, and 67.5 for this component. And when you add all this up, you get 87.95. So Joe's going to score about an 88% in his chemistry class. And notice if we go back and look at his grades, he did not score an 88 on any one component. He had a 65 here, he had a 93 here, he had a 90 here, and yet his aggregate grade, or his weighted average grade, is an 88%. Let's try another example. In this case, I tell you that boron 10 and boron 11 are the only two naturally occurring stable isotopes of boron, and I ask you to use the periodic table and the atomic weight found thereon to define or decide which one of these two isotopes is more abundant. And so we know that the mass of boron 10, and you'd have to look this up in a textbook to figure this out, but I do know that the mass of boron 10 will be very, very close to 10 AMUs. Remember, the mass of each nucleon is about 1 AMU. You have 10 of them there. The masses aren't exactly additive, but it's pretty close for our purposes. The mass of boron 11 will be very, very close to 11 AMUs. When I look at the mass that's reported on the periodic table, 10.81, I see that this is much, much closer to the mass of boron 11, so I know that a majority of the atoms of boron in the Earth are boron 11. Boron 11 must be much, much more prevalent than boron 10 because the atomic weight is so much closer to 11 than it is to 10. Alright, let's try another example. In this one, we're told that magnesium has 3 stable isotopes. We're given the abundance of 2 of them, the mass of 2. We're asked to find the mass of the third isotope, magnesium-26. And so in this case, we have to remember that if these are the only 3 naturally occurring isotopes of magnesium, that the abundance of the last isotope can always be found by taking the abundance of 100% and subtracting off the others. So if you do that, you get 11.01%. The mass of the third isotope can be found by using the weighted average and the atomic weight as reported on the periodic table. So if we look at the periodic table, we find that the atomic weight of magnesium is 24.31. And then we take the abundances and the masses of the other isotopes that we were given, and we simply plug them in to the formula for the weighted average. So the first isotope had an abundance of 78.99. That translates into 0.7899. The mass of that isotope, magnesium-24, is 23.98504 atomic units. Then we sum up the mass of the next isotope. Forgive me if I do it down here. I'm running out of space here. These problems are wide. The next isotope was 10% abundant, 10.00, which translates into this here. And the mass of that isotope, magnesium-25, is 24.98584. 98584 atomic units. The last isotope, we don't know very much about that one. We know that its abundance is 11.01%, but we don't know its mass, so for now we'll just use an X. But we do know that we can use this formula and find the mass, because this is what a weighted average means. So in order to solve this, we simply must evaluate each of these terms. If I evaluate this term, I get 24.31 atomic units is equal to 18.94578. Atomic units. And I have 4 significant figures here and a whole bunch here, so I want to make a note to myself eventually that I want to round to that 4. The next term I can multiply by 0.1 and I get 2.498584 atomic units. And then finally, I want to remember to also round this. This figure here has 4 significant figures, and this has a whole bunch, so I want to round this one to 4 as well. So I'll round to that 8 at some later point. And remember, I have the mass of the other isotope that I'm trying to find out, which is this other term here, 0.1101 X. Alright. Going on to the next screen, if I simplify what I have, I end up with 2.865 and some change, rounded to this sig fig here, is equal to 0.1101 X. Remember, X is the mass of magnesium-26, and when I solve here and round to 3 sig figs, I get 26.0, and remember I had this U here, so this is atomic units. This is the mass of magnesium-26. And so we see that the mass of magnesium-26 is approximately 26 atomic units, 26.0 atomic units. Of course, we kind of knew that anyway, but in this case, because of significant figures, we were forced to round this down to 3 sig figs. If you wanted to really find the mass of magnesium-26, there's better ways of going about doing it, obviously. Let's try our next example, and this is our last example. In this case, we're told that copper has 2 naturally occurring isotopes, copper-63 and copper-65, and in this case we're asked to find the abundance of each isotope. And so we can look at the periodic table and see that the mass of copper, as reported there, is 63.55. And so we know that this mass is much, much closer to copper-63 than it is to 65. So we know that copper-63 is going to be much more abundant. But how are we going to go about doing this? Because in this case, we're asked to find the actual quantitative data rather than just qualitatively, as we did in the case of boron earlier. We're going to need to know the mass of the isotopes, and I have it here. And we don't know the abundances, and so we're going to need to make some considerations for that. But we can set up our formula the same way as we always have. We know the atomic weight of copper, and so we can get off to the races here. 63.55 atomic units is going to equal the mass of the first isotope, 62.9296 atomic units. Well, what is the mass of, what is the abundance of this isotope? We don't know. For now, I'm going to use an X. The mass of the next isotope is given to me, copper-65, the mass of 64.9278 atomic units. What is the mass of this isotope? We don't know. But I've already used the variable X, and I can't force these 2 isotopes to be equally abundant. If I use X in each case, that's what I'm saying, Now we already know from the atomic weight that the isotope 63, copper 63, is much more abundant. I want to use the variable y. And in this case, you're really stuck unless you remember that these two variables, although seemingly unrelated, are in fact joined at the hip. The abundance of copper 63 and the abundance of copper 65 do not vary independently. If I take my variables here, x plus y, they must sum to give me 1. The meaning of that is we're told that all of the copper isotopes are either 63 or 65. Therefore, once we know the abundance of one, we find the abundance of the other. They must sum to equal 100%. So here I can make the variable substitution in the previous line and say, okay, that means that y is equal to 1 minus x. Alright, having done that, I can now take my previous line that I had here. I'll go on to the next slide to give myself some room. 63.55 atomic units is equal to 62.9296 UX, okay, plus 64.9278 atomic units times, and now instead of writing y this time, I'm going to write 1 minus x. And now my equation's down to where I only have one variable. The other thing that I can do for my convenience here is I can notice that all of these terms contain the atomic mass unit, so I can cancel u out of each of these terms, and that'll save me a little bit of ink as I move forward. 63.55 is equal to 62.9296x plus, now I have to distribute this number here through the parentheses, and so I'm going to end up with two terms here, 64.9278 minus 64.9278x. And now I have to collect like terms and simplify, as I learned in algebra class. I have to keep track of these sig figs as I do this, as I always do. Minus 1.3778 if I move this term here to the other side of the equation. What I find is that this guy equals 1.9982x once I collect these two terms here that have an x. So I collect the x with the x and the non-x, one without the x on it, collect those guys on the other side, and now I'm ready to solve for x. Excuse me, I'm missing a minus sign here. Of course, what this means is that x does not have any units on it. Well, that's okay, because remember that x is supposed to be the natural abundance of the isotope 63. Now let's go back here and check out our sig figs. If I count here and look at this figure here, has 2 decimal places, and this one here has 4 over here. So this figure here should be rounded to 2 decimal places eventually. This guy here has 4 decimal places. This one here has 4 as well. So I'm justified in keeping all of these. So when I actually divide and solve for x, I'm going to need to round to 3 decimal places, and I'll report that x, alright, x is equal to 0.690 once I round to 3. What does this mean, of course? 69.0%. That means that y, if I go back and remember that there were 2 isotopes I was solving for, y must then equal 31%, because these 2 variables are not independent. course. And if we go back and remember what these things were referring to, and sometimes it's helpful to make a note to yourself, X was the abundance of copper-63, and Y was the abundance of copper-65. And so, as we suspected, copper-63 is more abundant than copper-65. Just a quick note about the units of atomic weight before we finish for the day. You'll notice if you look at the periodic table, the atomic weights as listed do not have any units on them whatsoever. And that's because, for instance, if you look at carbon, 12.01, and then there's no unit given. That's because in its true sense, the atomic weight is actually a ratio. What we're saying is, remember, we defined the atomic mass unit as 12 AMUs were going to equal the mass of carbon-12. So if I take 1/12 of the mass of carbon-12, divide each one of these guys by 12, what I end up with is 1 AMU. So 1 AMU is 1/12 of the mass of carbon-12. And so when I look on the periodic table and see that the atomic weight of copper is 63.55, what I'm really saying is it's 63.55 times as heavy as 1/12 of the mass of carbon-12. And so in that way it doesn't, so if you want to think about it as 63.55 atomic units divided by 1 atomic unit, the units here cancel off. We'll talk more about that in a subsequent lecture. Just to give you a quick summary of what we talked about today, we defined the atomic mass unit, which has two abbreviations, AMU or U. We also defined the idea of the atomic weight. Thanks for watching, and I hope you have a great day.